talking about matrices, guys, and we're going back to basic stuff. Here, let me get the microphone out of the way. Such as dimensions. You're going to have to know about dimensions. You're going to have to know about adding, subtracting, multiplying, both scalar and matrix multiplication. Also, the rules on when you can multiply and when you can't, as well as the rules for when you can add and when you can subtract and when you can't. Those aren't too difficult. We'll talk about solving matrix equations. We'll talk about equal matrices. Eventually, we'll get the 2 by 2 matrix, solving matrix equations that involve 2 by 2 matrices. Those will be done by hand. They will not be done with the calculator. The graphing calculator will be used when we get to 3 by 3 matrices, so don't worry about those too much. Finding an inverse of a 2 by 2 matrix, well, that goes along with solving those 2 by 2 systems. The 3 by 3s we'll do by hand, as I said earlier. Reflections and rotation matrices. We haven't talked about that yet, but we will, as well as compositions of those. So when we start dealing with composites of those, as well as size changes and scale changes. I didn't write those down. Well, here's your basic introduction. We start out by talking about the rows and columns, this being the number of rows and this being the number of columns. How do I read that? Well, there's 2 rows and 3 columns. So it's downright easy to figure that out, guys. Downright easy. Rows and columns. We use a capital A or a capital letter to represent the matrix. We use a lowercase letter to represent an element in the matrix. So I'm looking for the element in the second row, third column. So second row, third column. That is the element 0. Adding matrices. The rules for adding matrices, you can't add them unless they have the same number of rows and the same number of columns. That doesn't mean you have to have what we call a square matrix. Not necessarily square. Okay? So don't get it in your mind they have to be 2 by 2s and 3 by 3s. We can add those as well. This one is a 2 by 3. This one is a 2 by 3. My answer will be a 2 by 3. How many values are there in a 2 by 3 matrix? Yes, 6 of them. Okay, so we're going to figure those values out. It follows your common sense. 4 plus negative 3, 1. 7 plus 8, 15. 9 plus 1, 10. 3 plus 4, 7. 1 plus 0, 1, and 5 plus negative 2 is 3. So, exactly your common sense corresponding entries get added together. Is that true for subtraction? It certainly is. We can only subtract if we have the same rows and the same columns. We have, once again, a 2 by 3 matrix. 4 minus negative 3. Well, that turns into 7, right, because you're subtracting a negative. 7 minus 8, negative 1. 9 minus 1 is 8. 3 minus 4, negative 1. 1 minus 0, positive 1. And 5 minus negative 2 is 7. So there we have subtraction. Scalar multiplication is also easy. Scalar multiplication is when you multiply all the things on the inside by the number on the outside. So it reminds us a lot of the distributive property of multiplication. Okay? There's nothing different or unique or strange about that. Equal matrices. The only way 2 matrices can be equal is if their dimensions are equal. In other words, same number of rows, same number of columns. You can't have 2 matrices being equal which do not have the same dimensions. And yes, that does mean if this was a 2 by 3 and we had a 3 by 2, they could not be equal. Switching the rows and columns, you can't call them equal in that case. Well, I want to find x, y, and z. I've been told that these 2 are equal matrices. If that's the case, then x must be 2, right? Corresponding entries have to be the same. Y plus 2 also has to be equal to 4. So I can solve a small little equation in order to find out the y value is 2. I also can figure out that the 4z is equal to negative 3. 4z equals negative 3. So 1z has to be negative 3/4. Negative 3/4. So corresponding entries have to be the same. As you can see, the bottom row, 165, is the same for both of them. Let me review with you matrix multiplication just a little bit. We'll have to practice some of these in class, I know. First of all, we have the rules for matrix multiplication. You're not going to find this in a textbook, but I call this the inside number rule, which says that these dimensions must be equal. Otherwise, it's not possible. And if it's not possible, then on the quizzes or tests, you're going to write impossible, no solution, not possible, something like that. That tells me that you understand the inside number rule has been violated and we can't do the multiplication. The second rule is called the outside number rule, and you'll never find those names in books because I made those up. Outside number rule, just the names, not the rules. The outside number rule states that these are the dimensions of the product. These are the dimensions of the product. So we are going to have a 2 by 2 answer when we are done. And we know that a 2 by 2 answer has 4 entries in it, so that's what we're looking for. Now, how difficult is this? We are doing rows of the first matrix times columns of the second matrix. And it goes by corresponding entries. We've got a 4 and a negative 2. That makes negative 8. Plus 7 times 0. Plus 6 times 4. So my very first entry is 16 when I add those three together. Well, stay with the first row and move on to the next column. But you're going to do the same thing, corresponding entries. 4 times 5 is 20. 7 times 7 is 49. 6 times 8 is 48. And who in the heck put these big numbers in here? 69 plus 48. What do we got there? 100 plus 17. 117. Now that we're done with that row, let's move to the second row, and we'll go back to the first column. By the way, if I'm using the first or the second row and the first column, which entry do you think that's going to be in my new matrix? Probably the second row, first column entry. That makes a lot of sense here. 3 times negative 2 is negative 6, plus negative 1 times 0, plus 9 times 4. 36 minus 6 is 30. Last, I've got 15, because I'm doing second row, second column, negative 7, and positive 72. So what does that make me? 87, take away 7 is 80. So there's your final answer when multiplying those together. So it's always rows of the first and columns of the second, and I know we'll need to practice more of that in class just to refresh your memory. Solving a matrix equation. We'll start with some easy ones. This is done a lot like, except matrix. This is a matrix. It's not a variable. It's a matrix. So keep that in mind. Well, the first thing we need to do is add this matrix to the other side. Don't change any of the signs in between or in the matrix. All we're doing is adding it and getting rid of it from that side. So 2x is going to be equal to 11. 11 negative 1 and 4. Just like we would do in any other time, we would divide by 2 or multiply by 1/2. And so matrix X is 11 halves, 11 halves, negative 1/2, and 2. Sorry, let me move that up so you can see that. Yeah, if you couldn't see, because I didn't have that before, I moved that matrix to the other side. By adding it, I moved it to the other side. My bad on showing you the good old notes. Next question, is matrix multiplication commutative? Commutative means switchable. So let's see what we have here. We've got a 2 by 2 and a 2 by 2. The inside number rule is satisfied. Okay, so we can do this, and the answer will be a 2 by 2 answer. That's based on the outside number rule. Okay, so row times column, we've got 18 plus 28, giving me 3846. You know, just for fun, I'm going to switch these two matrices and just figure out the very first entry. Because if it's not 46 like the last one, then I know the answer to this question. So we've got row times column, we've got 18 plus negative 1. 18 plus negative 1 is 17. So the answer to this is no, and I don't have to go through the process of finding everything else in this matrix because I've already got the answer to my question. They can't be commutative because I already see that 46 and 17 are not equal. So they are not commutative. You can't switch them up and get whatever and get the same result. Now that does happen in certain situations, but not in all situations, so we can't claim that. The next things I'm showing you are capital I. That stands for the identity matrix, and this is a 2 by 2 identity matrix. This is a 3 by 3 identity matrix. What I want you to notice is that along the main diagonal, yes, that's called the main diagonal, we have ones. The main diagonal has ones. Everywhere else is zeros. So I could ask you for a 4 by 4 identity matrix, and you would just put ones down the main diagonal and zeros everywhere else, and you'd get the correct answer. What happens when you multiply by the identity matrix? Well, we've got row times column. That's 2 plus 0, which gives me 2. And row times column, which is 3 plus 0, which gives me 3. And row times column, 0 plus 9. And 0 plus negative 7. Oh my goodness, it's the same matrix we had before. Yes, because it did not change the identity of the matrix. Alright, well what about if I switch it around? Will it make any difference? If I start with another matrix and I multiply by the identity this way. Okay, multiply these two together, we get 4 plus 0. Row 1, column 2, 0 plus 5. Wait a second. Did I just do something wrong? Okay, had a senior moment, even though I'm only a junior. Ha! So 0 plus 5 is 5. I'm alright. You can't hurt me. Then this matrix right here, I go down to the second row, right? Go back to the first column. That's negative 6 plus 0, negative 6. And 0 plus negative 1 or negative 1. Oh my goodness, it did not change the matrix at all, right? It preserved the identity of the matrix. And that concludes Lesson 1 Matrix Notes. See you in class.